Hi everybody, this is our lecture on section 5.1, eigenvectors and eigenvalues. Now, sections 5, 1, 2, and 3, which is all we cover in chapter 5, there's a lot of theory in there, but not quite so much computational content. So I'm going to go through it a little more quickly this chapter than we normally would go through such sections. Okay, eigenvalues and eigenvectors. Definition. Given an n by n matrix A, an eigenvalue is a scalar k such that there is a vector v with a times v equal to k times v. So the matrix times the vector, it just scales the vector somehow. Okay, the vector v is called an eigenvector for eigenvalue k. Okay, so for example, if I take this matrix, 1, 0, minus 1, 1, minus 3, 0, 4, negative 13, 1, and I multiply by 1, 1, 3, well, let's see what we get. We have 1 plus 0 minus 3, so that's minus 2. 1 minus 3 plus 0, so that's minus 2. And then 4 minus 13 is minus 9, plus 3 is minus 6. Right? And this is equal to minus 2 times that original vector, 1, 1, 3. Right, so 1, 1, 3 is an eigenvector for this 3 by 3 matrix, 1, 1, 4, 0, minus 3, minus 13, minus 1, 0, 1. So that is an eigenvector for this matrix with eigenvalue minus 2. So that's the scalar that you get in the end there, minus 2. Okay? Now, suppose that we know k to be an eigenvalue for matrix A. How can we find all eigenvectors for this eigenvalue? Okay. Right, well, if A times V, so let V be an eigenvector, if V is an eigenvector A with eigenvalue k, then A times V is equal to, by definition, k times V. So, A times V is equal to k, and then just let's put the identity matrix here. The identity matrix times V is just equal to V. So let's just put it in there. So move this to the other side. AV minus KIV equals the zero vector. So now let's factor out V. A times V minus K times I times V equals 0. So V is an eigenvector for A with eigenvalue K if and only if V is in the null space of that matrix there. Oops, I was supposed to factor out the V. I didn't factor out the V. So you the V in both terms, so I factored it out. A minus KI. Alright, so we call the null space of A minus KI the eigenspace for A with respect to K, eigenvalue K. Alright, and then note that the dimension of this is at least 1. The dimension of the null space of A minus KI is bigger than or equal to 1 because it does have at least one eigenvector in it. But the eigenvector can't be 0. That's part of the definition. An eigenvalue such that there is a vector v not equal to 0. Right. The vector v is called an eigenvector. So yeah, you can't have a 0 vector because the a times the 0 vector is always 0. So, but that's always true. And we're talking about some special instance. So we don't use the 0 vector as an eigenvector. So when you're calculating this eigenspace, right, the null space of A minus Ki, you know if you already have an eigenvector, you know that you're going to get at least one vector in there. So, for example, calculate the eigenspace for this matrix 4, 2, 5, -1, 1, -5, 2, 4, 13 for eigenvalue k equal to 3. Find a basis for this eigenspace. Okay, now you're not guaranteed to have, so the dimension of the eigenspace, right, there's at least one eigenvector in it, right, non-zero eigenvector in it. So the dimension is at least 1. Okay, so a basis is going to consist of at least one vector, but you may not have any more than that. You would like that it has more than that in some cases, and we'll discuss that. But anyway, so here's an example, and the basis is going to have the eigenspace is going to have dimension 2. Okay, so here's the matrix A. So A minus Ki is equal to 4, 2, 5, negative 1, 1, negative 5, 2, 4, 13, and then K is excuse me, 3 minus 3, 0, 0, 0, 3, 0, 0, 0, 3. So this is equal to 4 minus 3 is 1, 2, 5, minus 1 minus 3 minus 2 minus 5, 2, 4, 13 minus 3 is 10. Right? So we want to calculate the null space of that. Right? Of not this, but A minus 3I equal to, right, that matrix right there. So we need to row reduce that guy. 1, 2, 5, minus 1, minus 2, minus 5. I mean, you see how that's going to work, actually, right? I mean, each row is is just a multiple of row 1. So you just have this. Right, so x3 and x2 are free variables, and x1 is equal to minus 2x2 minus 5x3. So x1, x2, x3 is equal to minus 2x2 minus 5x3, x2, x3. So we have x2 times minus 2, 1, 0 plus x5 times minus 5, 0, 1. Right, so a basis for the eigenspace for A with eigenvalue 2 is this right here. Minus 2, 0, minus 2, 1, 0, and minus 5, 0, 1. So we have two linearly independent eigenvectors for that eigenvalue. Okay, you need not have two linearly independent. You have to only have at least one, but in this case you got two. All right. So that's the only calculation that you do in this section, really, is just calculating eigenspaces for a matrix with respect to a certain eigenvalue. But there is a theoretical result here that's very important. I mean, I'm not going to really hold you responsible for the proof of this theoretical result, but we need to know it and understand it, okay, because it's important, is the following. So if V1, V2 through Vn are eigenvectors for A with respect to distinct eigenvalues K1, K2, Kn, okay, then V1, V2, Vn are linearly independent. Okay? If you have vectors for the same eigenvalue, they might be linearly dependent. I mean, these are two vectors with the same eigenvalue, 2. Was it 2 or was it 3? It was 2. Wait. Oh, 3. 3. 2 was the original example with eigenvalue 3. All right, these are two linearly independent vectors with respect to the same eigenvalue in matrix. But you don't necessarily, again, have to have that because the dimension of the eigenspace might be just 1 rather than more than 1. But if you have distinct eigenvalues, k1 to kn, and an eigenvector for each one, then they have to be linearly independent. Okay, proof. So assume, by way of contradiction, so we're going to set up a proof by contradiction. Is this running? Yeah. By way of contradiction, that these vectors are linearly dependent. Now, remember what we were talking about back in the section on bases, right? When you have a linearly dependent set of vectors, right, you can keep tossing away vectors that are dependent until you get to a linearly independent subset. Okay, so akin to that is the following. Let W1 to Wn be a subset of V1 to Vn that is still linearly independent, or sorry, not M, N has to be something else, M. Let W1 to Wm be a subset of V1 to Vm that is still linearly dependent. But the removal of any one vector from W1 to Wm leaves an independent subset. Right, when you start with a linearly dependent set, you can chuck away a dependent vector and then ask again, are we independent or dependent? Okay, if we became independent, take that vector you chucked out and put it back in. Now, look at all the other vectors besides that one that you took out and put back in. Can you take out any one of those? That's dependent on the others and then still be linearly dependent. So you don't just chuck away any dependent vector. Chuck away the dependent vectors that leave you with a dependent subset. If no such vector exists, then you've got this set that you want here. This set that is still dependent, but removing any one vector from it leaves an independent subset. Okay, so you're really paring down this linearly dependent set in sort of the right way. There's a name for it. It's not really used in linear algebra in general, but it's called a circuit, believe it or not. So that's actually the name of the thing. Why one would call it a circuit is a long story, which we won't get into. Okay. So you have this special set, this circuit. It's linearly dependent, but removing any one vector from it leaves it an independent set. Okay. So we already used K. So let L1 to Lm be the associated eigenvalues, distinct eigenvalues for W1 to Wm. Okay, notice because W1 to Wm are linearly dependent, okay, there is vector A such that, well, let's not do it in terms of matrices. There are not A1 to AM such that A1 W1, this linear combination, A2 W2 plus AM WM is equal to 0. Right? Not all 0. Not all of them are 0. Some of them are not 0. But what does this minimality of the dependent set mean? Because it's the smallest possible dependent subset. Right? If I chuck away any one vector, it'll leave me with an independent subset. If A1 is 0, well, now, this is a linear combination of these vectors that's equal to 0. But that would mean that, like, the null space with these vectors as its columns, that would mean these guys are linearly dependent, but they're not. They're independent. So there is no linear combination equal to 0 other than the one that's all 0. Similarly, if I took away this guy, now that's going to be equal to 0, but it's not supposed to be because you took out the A2 or the W2. All right? So because every subset of W1 to Wm is independent, we get, in fact, A1 is not equal to 0, A2 is not equal to 0, all the way down to AM is not equal to 0. So not that A1 to AM are not all 0, or, some are non-zero, some are 0. No, they're all non-zero. That's what that minimality buys you. This minimal dependent subset. That's what it buys you, is that every entry, every coefficient in the linear combination equal to 0 is non-zero. Okay, great. Now, multiply both sides by A. So I have A times this is equal to A times 0. Alright, so, well, matrix multiplication distributes over such linear combinations. So this is A1AW1 plus A2AW2 plus AMAWM, and A times 0 is 0. Okay? Well, the W's are eigenvectors for A. They're eigenvectors for A. A times W1 is, and what were the eigenvalues? We wrote them down somewhere. Yeah. The eigenvalues were L1 to Lm. A1, A times W1 is L1, W1. A times WM is LM, WM. So this is equal to A1, L1, W1 plus A2, L2, W2 plus AM, LM, WM equal to 0. Again, by the minimality of W1 to WM, of dependent set W1 to WM, okay, either, all of A1, L1 to AM, LM are 0, or none. Of A1, L1 to AM, LM are 0. Well, it has to be none because the A's were not 0. So because A1 to AM are all non-zero. Yeah. And what about the L's? They were distinct. Because, right, the A's are all non-zero and the L's are all distinct. Well, maybe one of the L's is 0, but it can't be because of that minimality thing. It must be that A1, L1 through AM, LM are all non-zero. Okay, now, if I take this linear combination here, both of these linear combinations, there we are. So I'm going to take this linear combination, which is equal to 0. So let me stretch this. No, it's just right. Just stretch it a little bit. And let's take this one and stretch it a little bit. Perfect. Take this one and multiply by L1. But this guy was equal to 0. So that's just L1 times 0. And I'm going to take those things and subtract. I'm going to subtract those two guys. So I have A1, L1 minus A1, L1. So A1, L1 minus A1, L1 W1 plus A2, L2 minus, well, A1, A2, L1 minus A2, L2. So this is A2, this first one is 0, okay? Plus, this is going to be A2 times L1 minus L2 times W2. Plus, this here is going to be AM times L1 minus LM WM. That's going to be equal to 0. Move this over a little bit so it matches up. Fine. Right? So this minus this is L1 A1, this is L1 A1, W1. Subtract those, you get 0. But here, this is A2 L1, this is A2 L2. So this is A2 L1 minus L2, W2. And then this, when you subtract, is AM L1 minus LM, WM. But, you know, again, W1 to WM were linearly dependent. Minimally linearly dependent. So by minimality, W2 through WM are linearly independent. Okay, but well, how did that happen? By minimality, W2 to WM are linearly independent. Okay, so we must have that A2 L1 minus L2 is equal to 0 all the way out to AM L1 minus LM is equal to 0 as well. But, come on. Right, L1, L2 through LM are distinct. And A2 through AM are non-zero. So A2, L1 through L2, L1 minus L2 is not 0. And all the way through AM, L1 minus LM is not 0. Right? It can't be 0. The A is not 0. And L1 and L2 are not the same, so that's non-zero. So that's a contradiction. All right, so that's the end of that proof. Let's do a quick example of that, okay, just so we can see. So let me just make an example not on film here. Okay, so the matrix A equal to 0, 0, negative 4, 1, 0, 4, and then 0, 1, 1 has eigenvalues 1, 2, and minus 2. So let's find an eigenvector for each one. For each eigenvalue, and we will know that these three eigenvectors will be linearly independent. Okay, so let's do this as fast as we can. So 0, 0, minus 4, 1, 0, 4. So we'll start with lambda, or k equal to 2. So this is for eigenvalue k equal to 2. 0, 1, 1 minus 2, 0, 0, 0, 2, 0, 0, 0, 2 is equal to, so minus 2, 0, minus 4, 1 minus 2, 4, 0, 1 minus 1, like that. And we want to do row reduction of this. So I'm going to multiply this row by negative a half. That's going to give me 1, 0, 2. And then subtract that from this row. So 1 minus 1 is 0, minus 2 minus 0 is minus 2, and then 4 minus 2 is 2. 0, 1 minus 1. Right, and then I'll flip these two rows around and subtract. 0, 1 minus 1, 0, 0, 0. Right, so x3 is free. x2 is x3. And x1 is minus 2, x3. So the eigenvector x1, x2, x3 is equal to x3 times minus 2, 0, 1, 1. So minus 2, 1, 1. So there's my first eigenvector. Let's check it real quick. 0, 0 minus 4. 1, 0, 4. 0, 1, 1 times minus 2, 1, 1 equal to, so 0 plus 0 minus 4. Right, it's eigenvalue 2. Minus 2 plus 0 plus 4 is 2. And 0 plus 1 plus 1 is 2. Right, so that's 2 times minus 2, 1, 1. Right, so there you go. So that's correct. This vector is the same as that vector, so that checks out. So why don't we actually leave that in there? I was going to just eigenvector, let's check. Right, and when we checked, we got that this is 2 times that. Or this is 2 times that. Okay? So that was k equal to 2. K equal to negative 2. So 0, 0. Let's see. Copy this here. So this time the eigenvalue was negative 2. So this turns out to be a plus 2, 2, 2. So this is 2, 0, minus 4. 1, 2, 4, 0, 1, 3. Okay, so I'll multiply that by a half. And then I'll subtract that row from this row. So I have 1 minus 1 is 0, 2 minus 0 is 2, and then 4 minus minus 2 is 6. 0, 1, 3, right? Divide this, so we get this. 1, 0, minus 2, 0, 1, 3, 0, 0, 0. Right, so x3 is free. x2 is minus 3x3, x1 is 2x3. So x1, x2, x3, that's going to be equal to x3 times 2 minus 3, 1. Alright, so that's eigenvector number 2. And let's check. So 0, 0, minus 4, 1, 0, 4, 0, 1, 1 times 2, negative 3, 2 minus 3, 1 is equal to 0, 0 minus 4. It's supposed to be negative 2, right? Negative 2 times 2 is negative 4. And then we have 2 plus 0 plus 4 is 6. And then 0 minus 3 plus 1 is minus 2. Alright, which is equal to minus 2 times that factor there, 2 minus 3, 1. So that checks out. Right? This factor is minus 2 times, well, this factor is minus 2 times that factor. Okay, and then one more eigenvalue is negative 1. Or it was just 1 itself. Alright, so we're going to do the matrix A minus 1 times I, which is just I itself, is equal to minus 1, 0, minus 4, 1, minus 1, 4, 0, 1, 0. Okay, so add this row to that, so I'll negate this. 1, 0, 4, add this row to that, I have 0, minus 1, 0, 0, 1, 0, so we get 1, 0, 4, 0, 1, 0, 0, 0, 0. Alright, so x3 is 3, x2 is 0, and then x1 is minus 4, x3. So eigenvalue x1, x2, eigenvector x1, x2, x3 is x3 times minus 4, 0, 1. Alright, so there's my eigenvector. Let's check. So that's 0, 0, minus 4, 1, 0, 4, 0, 1, 1, minus 4, 0, 1. So I'm going to multiply this and get the same vector back. So that's 0, 0, minus 4. 0 plus 0 minus 4. And then this is minus 4, 0 plus 4, 0. 0 plus 0 plus 1. Alright, so there you go. Okay, so the three eigenvectors that we got, so what were they? Minus 2, 1, 1. Not vectors, but eigenvectors. 2, negative 3, 1. And minus 4, 0, 1. For eigenvalues, 2, minus 2, and 1 must be linearly independent. I don't even need to check it. I mean, we could check it, but I'm not going to. Okay? So we know that they are, because these are distinct eigenvalues. 3 distinct eigenvalues for these 3 distinct eigenvectors. And what our theorem says is those are always linearly independent. So there you go. Okay? So that is the lecture on this section.